Hi there, welcome at my digital poster, which is about using machine learning to obtain water mask from Sentinel-1 images, and then using this mask jointly with Sentinel-3 altimetry to improve the measurement of water heights at lakes and rivers. This work is also fully applicable over sea ice, so as to verify and validate the measurement of freeboards by the altimeter. Let's browse this presentation quickly. This work is carried for ISA-funded projects. About altimetry for hydrology, the main objective is to measure the water heights in the lakes and rivers that are crossed by the altimeter ground track. Before Cryosat 2, altimeters had a relatively short repeat period of 10 to 35 days, and most of the work were focused on repeated crossings at the same place, which was called a virtual station. Processing altimetry data at the virtual station was relatively simple. It was just a question of identifying from a static water mask the range of latitudes to be considered for each pass of the satellite, and then exploit the series of records over water. In particular, one of the steps is to use a 1 point per crossing filter, which is the median filter among all of the records above water. Cryosat 2 introduced a very long repeat period of 369 days. And the concept of virtual station is vanishing, and it's much better to exploit all possible crossings of the river by the satellite ground track. And this case is also similar with the case when we are at the end of phase of altimetry mission and the satellite is in drifting orbit. In both cases, we want to exploit as many crosses as possible, and we want to automate it. And Alongtrack has introduced a new framework. Alongtrack SAS, which is a company actually, has introduced a new framework for IT hydrology based on updated water masks. Let's go about the principle of water height measurement. Basically, it exploits the altimeter altitude and the retracted range, as well as corrections. In this methodology that we introduced, we are going to choose a Sentinel-1 image, co-register it with a clear sky Sentinel-2 image, and with the Sentinel-2 image, we obtain an RGB image from 3 channels, and this RGB channel is exploited to manually delineate some polygons to define the water and the land classes that are going to serve for 2 purposes: training and testing of the machine learning algorithm. The Sentinel-1 pixels falling under these polygons are going to be used for both the training. We're split in 2 parts, one for the training and one for the testing. And after that, we are going actually to to perform the training in 3 different cases. First case is when we are using as feature only the VV polarization. Second case is only VH polarization, and third case is VV and VH polarization. Here is the dataset, and here is the methodology using both Sentinel-1, Sentinel-2 images to perform the training and also to validate the results of the Sentinel-1 from the Sentinel-2. At the end of this process, we identify that the case when we are using V and VH together is the best one, and this is the one that we are selecting for producing the water masks. After this step, we have a new water mask, which is called the S1WM, Sentinel-1 water mask, and we are comparing it to the very old SRTM water mask, which is called SWBD. If we look at the crossings and if we display these masks together, we see that there are quite some changes. And we are going to show how the intersection of the altimeter ground track varies according to this water mask and the difference in results. In the end, we will get this table, which shows that when using the new S1WM mask, we are getting some quite different results than the one obtained with the old water mask. And this means that there is quite some margin in this process, and we are going to analyze this further down and to scale this at a larger number of images and Sentinel-free tracks. But it looks to be a promising direction for improving the water height level. I'm looking forward to have your visit at my poster. Thank you very much.